So 4.9 starts to talk about exponential and logarithmic equations. There are three facts about exponential and logarithmic equations that will be helpful. The first fact here, if you can get the bases to match on both sides, you can drop away the bases, and then you know that the powers must be equal. So this just means if you can get the bases to match, you can drop away the bases and the powers will be equal. So that's a very important tool. What that means is if you know, let's say you get 2 to the 5th equals 2 to the x, we know that 5 is equal to x. And I've kind of subtly, I've done that sometimes as we've gone through it, but it's an actual property of equality. The second fact right here is that if you can get both sides contained into the same logarithm base, the whole side has to be in there, you can drop away the logarithm. Example, if I have the log base 2 of x equals the log base 2 of 7, I know that x is equal to 7. So it's just a very simple kind of thing, okay? For number 3, let's say we know that 7 is 2 to some power, and we want to solve for the power. We can take and we can say that it's the log base 2 of 7.
For the late interruption, I just wanted to remind everybody that we have CTSO meetings this morning. Skills USA Juniors, you'll be in the cafeteria first period. FFA is in the McLean Lecture Hall. BPA will be second period in the McLean Lecture Hall. And then Skills Seniors, you are 12:45 this afternoon in the cafeteria. Thanks.
Now, if we can't get the bases to match like this, or if we can't get the logarithms to match like this, there is another technique that we will use. And it's kind of based upon this, and I'll show you how to do that, okay? Now, we're a little bit limited. We don't know, and I'm surprised that maybe they give the formula later on, but there is what's called a change of base formula. And if we need it, I will show you how to use that formula. But for now, let's talk about problem number 1. Now it says to solve each of the following equations, find the exact answer, and then use your calculator to approximate the answer to the nearest 1,000, 3 decimal places. So if we look at this first equation, we unfortunately can't get the bases to match. When the bases don't match, okay, I'm going to show you 2 techniques. The first technique we're going to use is we are going to put a natural log on both sides. So when the bases will never match, put a natural log on both sides. Now, the reason we can do that, and the reason that that is helpful, is because then we have learned about the properties of logarithms that says we can drop that power down in front. So then, as soon as we drop that power down in front, we get that the natural log of 4 is x times the natural log of 3. Now, why is that helpful and important? Well, the natural log of 4 is just a number I could put into my calculator. The natural log of 4 is just a number that I could put into my calculator. So I could just put the number into my calculator. So I would find that x would be equal to the natural log of 4 divided by the natural log of 3. Now, we only know how to combine logarithms or use rules of condensing for addition and subtraction. Division doesn't allow us to mush them together. So that's your answer. Now, that would be considered our exact answer. That's exact. That's exactly what it is. But if we wanted to throw that into a calculator, we would get that x is approximately to 3 decimal places 1.262. So if you want to try it on your calculator, on the red calculators, you would hit the natural log of 4, make sure you end the parenthesis, divided by the natural log of 3, end that parenthesis, and if you hit equals, you would get 1.262 when rounded to the nearest thousandth. Now, that is what we can do if the bases don't match. I'm going to show you another technique using one of the facts from up above. The third fact that hopefully you wrote down was that if we have a number equals a base to some power, we can convert it to a logarithm. The log base b of the number equals the power. So let's take that same exact equation we saw, 4 equals 3 to x. Our number is 4, our base is 3, our power is x. And let's put it in logarithmic form. That would be that the log base 3 of the number 4 is the power. In this case, I'm sorry, it would be x. Now that's the exact answer also, but most calculators don't have a button for that. So I am now going to show you a fourth formula that's going to be helpful. It is called the change of base formula, and it allows us to put any kind of base into the calculator. And we're going to use natural logs. Okay, let me show you what that is. Okay, the change of base formula says if you have the log base b of some number and you want to throw it into a calculator and you don't have a log base b button, you can take the natural log of the tall over the natural log of the small. That's a silly little rhyme to help you remember, but it's just the natural log of the number divided by the natural log of the base. Look at what we had over on the side. For this particular function, our number is 4, our base is 3. So x would equal the natural log of the number over the natural log of the base, which is exactly what we got over there. So the change of base formula is super helpful, wonderful, great. It would still be this is the exact answer or this is the exact answer. iMath would accept either one. Those things are exact. I think it will. We'll find out in a little bit. But both ways that we do the problem, we're going to get an approximation of 1.262. Both ways. Now, I like doing this way, tack a natural log, drop the power, divide, because then I don't have to use one more formula. But it's completely your decision. Now we have one more formula. So those 4 formulas are what we're going to use as we go through this process when solving equations with logarithms. But this allows us to put any base in a calculator. So if I have the log base, even if you did on your calculator, the log base 7 of 49, we know the answer, it's 2. But that's just the natural log of 49 divided by the natural log of 7. You're going to get 2. So it's just a really super helpful formula because it allows you to do any type of logarithm by using a button that we already have on our calculator, okay? Now, let's take a look at B. B is, it's a problem that we saw a very similar one, I think, in our homework. I think it was 4A day 2. The problem with this is before you use any of those formulas, we must isolate the base part. The fact this 1.75 is there is going to cause us issues. So you have to divide by 17.5 first before you do anything else. Now, 22.4 divided by 17.5 does have an exact decimal that isn't too horrible. So I'm just going to change that to 1.28. Now, remember, there's 2 ways you can approach this. Our base is 3.4. Our power is x. Our number is 1.28. So this is the log base 3.4 of the number 1.28 should equal the power x. That's the solution that's exact. Now, how could we enter that into a calculator? Well, it's the natural log of the base, no, I'm sorry, the natural log of the number divided by the natural log of the base. So we could have done that even right here. What's our base? 3.4. What's our number? 1.28. Natural log of the number over the natural log of the base equals the power. The natural log of the number over the natural log of the base equals the power. Let's add to our little formula over here that this is equal to the power. Okay. So both of those are the exact version of our answer. So our answer now, if you throw it into that calculator, our power is approximately 0.202. Whether you use that as your exact answer or that as your exact answer, both of those are going to work. So please make sure that you know that formula, use that formula. It's very helpful, okay? So those are the main ones. But what we need to do is we need to practice lots of different types of formulas that might come up, and then we'll actually look at some word problems. So let's look at 2A. Now, they throw a log on both sides. I tend to throw a natural log on both sides. It doesn't matter. It's going to work both ways. So let's stick a natural log on both sides. Now, if in the instructions they say for iMath they use log, this technique works. You can just throw a log on both sides. I'm going to use natural log. I don't know why. I just have always done it like that. Now, we do that so we can take this power and we can drop it down in front based upon our power rules we learned about logarithms. So this would be x times the natural log of 5 equals the natural log of 800. So we get x equals the natural log of 800 divided by the natural log of 5. Now again, that's your exact answer. And we can take the log of both sides as long as both sides are positive things. If one of the sides was negative, you can't do that. If one of the sides was 0, you can't do that. We can't inflict a logarithm on anything but positives. But both the 5x will be a positive thing. The 800 will be a positive thing. So we can do that. But we could immediately looked at this and said that the power is the log of the number divided by the log of the natural log of the base. So the power would be the natural log of the number divided by the natural log of the base. We got that either way we did it. And then B, just remember, you can't take log of negative or 0. Can't do it if one of the sides is negative, if one of the sides is 0. Nope, can't do that process. But most of the time, that's not going to be the case. Okay? So that's just two different ways to approach the same problem. Again, you don't have to use natural log. You can just write the word log. Both of those are options on our calculator. As long as you use one of the buttons that's on our calculator, whether it's log or natural log, you're good to go, okay? So that being said, let's move on to some word problems. I would like to jump to problem number, do I want to do 3? Well, usually when they have the little star, that means there's problems coming up. Yeah, why not? Let's do 3. Okay. It says in 2023, the enrollment of at Mainland High School was 1,650 students. Administrators predict the enrollment will increase by 2.2% each year. Determine when the enrollment is expected to reach 2,600. Okay, so first let's just think about the setup of the equation that we would use for this. We're going to use a function of time. Remember, it's always our starting value times 1 plus our rate, and then to a power of t, are the basic yearly, if they just say it increases at a rate of something per year. This only works if they say it's a per year. So the starting value was 1650. The rate was 2.2%. Let's write that as its decimal equivalent. Just move that decimal 2 places to the left. That's why we got 0.022, and then t. And so our function for this particular situation would be 1650, 1.022 to a power of t. Now we want to know, when will the enrollment reach 2600? So when will our function reach 2600? So 2600 would equal the function in question. So that's where we're starting here. The problem is that 1650 cannot be there for us to use any of our techniques we've learned so far. So you first have to divide everything by 1650. Now, if 2600 divided by 1650 does not give us a decimal that stops and is pretty, which it does not, you can either reduce the fraction, or you can just leave it 2600 over 1650 for the rest of the problem. I don't care. It doesn't matter. It does actually reduce to be 52 over 33, just so smaller things to write. And that's equal to 1.022 to a power of t. Now, I'm going to use natural logs again. I like to do that. I don't know. But let's think about the formula that I gave you earlier. The power is always going to be the natural log of the number divided by the natural log of the base. So our power of t is always the natural log of the number. Now the number is 52 over 33. So I have to take the natural log of that fraction divided by the natural log of the base. So that's the exact answer. Okay, that's the exact answer, and that would be years. Our time was every year this happens, so it would be years. So that's our exact answer. But this is a real life sort of example. For real life examples, a number like that doesn't give us as much information as the actual decimal. So if we put this into a calculator, that's the beauty of using that natural log or a base 10 log, is we can throw into a calculator. We get approximately 20.9 years. So we could say that about 21 years later, so in about 2044, the enrollment should be at that level. We're talking about that 2,600 students. So that is that. And I don't care about B. Okay. So now let's jump to number 4. So number 4 says, remember the alpaca problem we had done? It says that after 8 years, the alpaca population decreased to 187. Assume the number of alpacas decays exponentially to find a function that expresses the number of alpacas on the farm in terms of the number of years since January of 2016. If n is the number of years since January of 16, so let n be our years after 2016. And then if we think of the fact that our starting population, we had a formula. We had made a formula. And let me remind you what that formula was. It started at 218. It was decreasing. So we got an 858. Remember, if it's a decreasing, that thing will be below 1. If that number is between 0 and 1, it's decreasing. If that number is more than 1, it's increasing. And then it's a power up. This is after 2018. And you see how it's every 8 years. So don't forget, if we just want to put in years, you got to divide that by 8. So we had found that actually in the thing we had done. It was investigation 4.4. Okay, so we have this function. It says, using the function, estimate the number of alpacas on the farm in 2025. So if we are going from 2016 to 2025, if you just subtract, that would be that our n is 9. 2025 minus 2016 is 9 years. So you're just going to plug in 9. So if you're inputting time, you just get to input. You don't get to have to worry about actually solving. It's just input. What do you get? Okay. Now we get a funky decimal. The approximate decimal is 183.449. For real life things, just use the whole number, cut off any decimal. Maybe that's a baby that's hasn't been born yet. I don't know. A baby alpaca. So we could expect 183 alpacas to be on the farm in 2025. Okay. Here's where C is where the technique isn't as nice, because we are going to go backwards. Okay. So now let's refer to C. Now let me write that equation from A so we can see it a little better. It says, using algebraic methods, let's determine the number of years on the farm when the alpaca on the farm reaches 165. So we know we want the total now to be 165. So that goes here. And so I'm such a good handwriter. Okay, so anyway, so just take our equation, set it equal to 165. So again, we have to divide off that 218. That's always the first step. You always end up dividing by your initial value. So get used to that. That is the thing. And now we can use our change of base formula, which I'll write over here. Remember that the power is always the natural log of the number over the natural log of our base. So in this particular case, the power, n over 8, is the natural log of that 165 over 218, our result, divided by the natural log of the base. Okay. Now, we need the n. What are we going to do to get rid of the 8? What can we do to get rid of the 8 algebraically? What could we do to get rid of the 8? What do you think? It's just an algebraic equation. If we have that n is divided by 8, how do we get rid of the 8? Yeah, we're just doing the opposite, multiplication. So multiply both sides by 8. I'm going to put it up at the top. Multiplication, that would be 8 over 1, so it would go on the top of our fraction. So the exact answer of years, it would be 8 times the natural log of that gross fraction divided by the natural log of our base, 0.858. Now that's the exact answer. Be very careful as you enter that into a calculator that you could even put the top and the bottom in parentheses if that helps things. But the n is approximately 14.550 years. So about 14 and a half years, we would expect that we would have 165 alpacas. Now, if they wanted what year that would happen, remember we had been starting at 2016. If you add 14 to that, that's 2030. So, you know, in the middle of the summer of 2030. So it's 2030, June of 2030, if you really kind of wanted to be a little more specific, halfway through 2030. Okay. Let's now do one more word problem, I think. I think we'll probably just do one more. We'll see. Do I want to do 6? No, but I want to do 5. Okay, let's do 5. And that's the last one we'll do for this investigation. It says at the beginning of 2020, the population of Diamond Bar was 45,000 and the population of Chino Hills was 37,000. At the beginning of 2022, the population of Diamond Bar was now 51,750. So you see that population was going up. The population of Chino was also going up, 44,400. Assuming both cities grow exponentially, how many years will it take for the population of Chino Hills to surpass the population of Diamond Bar? So really kind of an interesting component there. So do you see how it went? It was a two-year, they measured it 2 years later. So make that note. If it was 1 year later, we wouldn't have to worry as much. But let's set up each one, okay? So I'm going to call the Diamond Bar one just D. Okay. You put down their starting population first, 45,000. What is the rate of change? Well, it went from 5170, or if I can read the problem, so sorry, 51,750. It started at 4,500, but or 45,000. But that was a 2-year growth, so make sure to divide by 2. Okay, so that's a formula for Diamond Bar. Let's make up a formula for Chino, and you'll get the same sort of thinking. This is 37,000. Take the new population divided by the old population to get that 2-year growth. That's why we have to divide by 2. And we can even simplify it further. That's 45,000. This becomes a pretty nice decimal, 1.15. And this is 37,000. And this is 1.2. Now let's think about what we want to know. We want to find out when the Diamond Bar population will be equal, because then after that, Chino has a higher rate. It's going to go faster. So if we know when they're equal, we can then go from there. Okay. So let's put these two equations equal to one another, and I'll show you a technique that we can use. So let's get the things that have that t over 2 on one side, the things that do not on the other side, okay? So let's just move things around a little bit. So we would get 45,000 divided by 37,000. Let's just put 45 over 37. The zeros would cancel. And then we would have the 1.2 to a power of t over 2 over the 1.15 to a power of t over 2. And if those powers match, let's rewrite this as just 1.2 divided by 1.15, all to the t over 2. Now, if we just focus on these two pieces, this is our number, this is our base, this is our power. We can use that change of base formula. Remember, if we have a number equals a base to a power, I know that the power will always be the natural log of the number divided by the natural log of the base. So I can always do that technique. That change of base formula is always going to help me. So I know that our power, t over 2, is the natural log of our number, 45 divided by 37, divided by the natural log of our base, 1.2, divided by 1.15. Now, you'll see that t over 2 there. That t over 2, we saw one earlier like that. Just multiply both sides by 2, and you'll get what you want. So if you throw all that into a calculator, they're equal, it's about 9.2 years. So in 9.2 years, Diamond Bar's population and Chino Hill's population will be the exact amount. After that, Chino Hills has that 1.2 rate. It's higher than the other, so it's going to grow faster. So anything after 9.2 years, Chino's going to surpass the population of Diamond Hills. So there you go. That is an application for population. Population is a popular one. Bacteria growth, budgetary things. Those all come up in exponential word problems. So your 4-9 investigation has now been completed. Please at this time turn it in. Go into iMath, open up pre-class 4-9, which is on the calendar for today. We're going to do some of that together. Okay, so I'm going to split screen it so that we have some paper to write on so you can kind of see some of our calculations here. So go into your iMath calendar, open up pre-class M49 for me. We're going to do that together. And this one has some sliders, so I think, oh, well, let's just, let me show you that as we go. So at the top here, they've given you some examples. Those are always good to look at. Here they have a picture of what you're looking at. So that's the equation y equals 4 to the x. If x is 3.3219, the height will be 100. So let's go to, now my applet has a 3 to the power of x. I don't know what yours has. If it's different, that's okay. But let's see what it says. It says to complete part A, you must enter numbers only. The program will not accept expressions that represents the value. So we can't solve it exactly. We're going to have to get numbers. It says if you want to solve 3 to a power of x equals 200, we know that the solution will be greater than the integer blank, but less than the integer blank. Now let's slide I'm going to slide my applet over until I reach a height of 300. Now again, mine and yours might be different. But do you see how it is something for me that's in between 4 and 5? So I'm going to put that it's in between the integers 4 and 5, okay? Because my little purple X ended up somewhere between 4 and 5, okay? Because if you do exactly 3 to the 4th, if I can get it to get, if not, I'm going to do it on a calculator. 3 to the 4th is 81, I believe. Yeah. So 3 to the 4th is 81. 3 to the 5th is 243. So see how 200 is smack dab in the middle of those values. Okay. So 3 to the 4th is 81. 3 to the 5th is 243. Your number that's sitting right there, you'll see that our 3 to the x, that is between 3 to the 4th and 3 to the 5th. Okay, so that makes sense and that should work. Okay, now it says use the applet to observe the value of f of x, getting as close as you can to finding a height of 200. They've marked mine on the line. I'm going to go up and try to hit that line as close as I can. I can get to about 4.83 for me. Do whatever you think is best. But you see how it's a number between 4 and 5. Okay. And then it says check your work by entering 3 to a power below that represents your number, and the preview should show that you're super close to 200. So I'm going to put in here 3 to a power of that 4.83 that I thought it was in the step above. And you can see my preview is pretty darn close. It might yell at me. It might want 4.82 or something. It's a little big, but. Did I skip something? I have no idea. Okay, anyway, mine's gone. Okay. Well, that was, okay. So now, I have no idea. I have no idea. Oh, I don't know. Let's see. Let's try again. Okay. Okay, good. Okay, now, right here, do you see right there where it says use a graphing calculator or graphing program to solve each of the following equations? Okay, so I am going to close this for now. I'm sorry, it's not cooperating. Let me open up Desmos. You open up Desmos as well. And I'm going to put in the function 6 to a power of x. Okay. Now, see where it says, mine says 6 to a power of x equals 150. I want to know when the height is 150, when this function is equal to 150. So I'm going to type in, where does y equal 150? And I am going to see, I'm going to scroll until I hit 150. What is that point saying? Well, the x value would have had to have been 2.79649 for me. So I'm going to put in here 2.79649. 2.79649. Okay. And you should see that you could check it if you really wanted to. And so it worked because I used Desmos to find the accuracy. Okay. Now I'm going to put in the next equation. Be careful the way you put this one in, because I'm going to put the 7, and then I'm going to put in parentheses 4 to a power of x. Again, now this time I want it to reach a height of 1155. So I'm going to type, when will y equal 1155? And I could probably change it, but it's very large for me. Okay, so we'll see that line, that horizontal line appear at 1155. So then we're going to look and see where does it intersect it. And so for me, it's that 3.68316. So 3.68316. So that's how you would use Desmos to help you answer the questions for that. Okay. Now, for here, it says verify the solution above. So they've done this equation. They say that the answer is 4.419. And it says, look at the preview to see if its value is would be really close to 12 if you round it. Okay, so let's enter what they said there. So it's 2 times the quantity of 1.5, enter whatever yours says, to a power of, and they use parentheses everywhere, so I'm going to put it exactly like they did. And if you'll see the preview, it is super really close to 12. Okay, so that's what they wanted there. And then they showed you on the graph, similar to how I entered it into Desmos. Now, this bottom thing says type log base 4 of 57. So log underscore 4 parentheses 57. Type in whatever you need to type in there. And it says, look at the preview to see its value, 2.9167. Make sure you can justify why the value makes sense for this expression. One thing you can think about the fact is that 4 to the third power is 64. So if I'm trying to look for 57, it should be a number close to 3, but under, which it is. Okay. So what is the logarithmic expression that represents the solution to that equation? So remember the expression. So it says that it doesn't say equation. So I'm just going to go the log base 5 of 1006. The log base 5 of 1006. So our base is 5, our number's 1006. So whatever your numbers are, it would be accordingly. And then part 3 says, what is the logarithmic expression that represents a solution to that? Well, the base is 3, so I'm going to go log base 3 of the number 1452. So yeah, I got to put that 1452 in parentheses to show it's in my logarithm. And you can see that's what happened to the side there. Okay, so that is those ones. Now, finally, we're back to an algebra problem. For these last two, we're going to do together. So if you want to do yours and mine together. Okay. So my equation for this last section is 21 4 to a power of x equals 280. Now it says solve for x. You first have to divide both sides by 21. I'm not physically going to actually divide it. I'm just going to write, I don't know, 280 divided by 21. Then I'm going to switch it into logarithmic form. It is, the base is 4, the number's 28, or 280 divided by 21. So it is going to be the log base 4 of the fraction 280 divided by 21. And that's exactly what I'm going to put in there, the log underscore 4 parentheses 280 divided by 21. And make sure you use parentheses, okay? Now you saw how you could check that answer in Desmos, so you could check it if you wanted. Now look at B for just a moment. Let's do B together. In B, let me write this down. Can anybody tell me, for my equation, what's the number I have to divide both sides by? What's the number I have to divide both sides by? For my equation, what would I divide by? Exactly. So I have to divide that 48 off. So I get 16 divided by 48 is base 0.42 to a power of x. Now my base is 0.42. My number is 16 over 48. So the log base 0.42 of the number 16 over 48 has to equal my power. So I get to put that in there. So the log underscore 0.42 in parentheses, I'm going to put in 16 over 48. If I can find where my division bar, there it is. Okay, so that is your 4.8 pre-class. Okay, so that should be done. Now, we don't have much time, but even if we get one question done, that's better than nothing. So now go to your calendar, look at the homework on the 20th there. I'm going to do homework 4.9, day 1. Okay. I have to hit 1,000 buttons to get there, but if it allows me to go there. Okay. So these are word problems. I would like to do at least one together. So let's do our first problem here from homework 4.9, day 1. Question number 1 together. It says Kiana's car is worth $15,000. That would be our starting amount. At the beginning of 2000, it decreased exponentially 23% a year. So what's our function? Well, you always write that starting value. Now we're going down by 23%. 1 minus 0.23 or 100% minus 23% is 77%. So this would be 0.77 t. It did say yearly, so we don't have to adjust the t at all. Okay, so that's what I'm going to type over here. 15,000 times 0.77 to a power of t. Okay, so that's my function. Now I'm going to check it just to make sure that that's what they wanted so that I don't move on with something that's not correct. Okay, so that's what they wanted. It says, after how many years will the car be worth 6,000? So we're going to place the f of t with 6,000. We're going to divide both sides by 15,000. So 6,000 divided by 15,000 will be our base. Now, cross out the zeros. I think if we do that, 6 divided by 15, they're both divisible by 3, is the same as 2/5. So I know that 2/5 is 0.77 t. So remember how we solve that. The log base 0.77 of 2/5 will equal the power. If we just switch it into, and I think they're okay with us not giving an exact number at this time. So I'm just going to plug in the log base, so my underscore, 0.77 in parentheses 2/5. I think they'll be okay with me reducing it. And they were fine with that, okay? So there you go.